Hello everybody, welcome back to my series on nanoarrow. Really excited for this video. In this one we are going to start working on computations. So in the first video we did some computations, but it was just on a single array. In this video we're going to scale that computation to work across an entire data frame, table, whatever we want to call it, and have it scale to be out of core, right? Meaning it can scale to data sets that are larger than memory. So we'll see that just to show you this here. I'm going to go ahead and use a PyArrow data set and memory map something. I have this big file .arrow here, which is 81.3 gigabytes of integral data. I am not going to be able to load that into a data frame, but what I could do is take something like that, run it through my sum function. As you'll see, my memory is not going to increase really all that much up here, but I'll get through this 80 gigabytes of data and we'll see a result calculated back of all the integers located in this file. And there you have it. I was able to sum that entire array, even though it was 80 gigabytes of memory, without really using all that much memory on my end. So let's see how we did this from scratch. Okay, so before we jump into any code, I want to take a couple minutes and talk about terminology with PyArrow and Arrow in general, because I think it can be really confusing. And PyArrow and nanoarrow do not use the same terminology. So it's easiest if we just kind of jump in to PyArrow and start looking at this. I think the basic thing we went over the last time was just a plain arrow or a PyArrow array. This is kind of like, I don't know if you use pandas or NumPy, just a contiguous set of numbers in memory, and they expose to some kind of API. Now, the first first video in the series we did just work with an array, but that's a little basic for Arrow. So there's a couple other objects we can look at. One is a chunked array, which kind of looks like an array at face value, but actually has, potentially different chunks that can be anywhere in memory, or even not in memory. They're really just allowed to be kind of any sequence of objects, and this is more of what you would consider a stream. So when we were working with an array, we saw we had an arrow C array, dunder for capsules that gave us a schema and array. But with stream objects, which a chunked array is one of, you get this arrow array stream back. We're going to look at that in detail when we jump into the code. But a chunked array is still just one array. So kind of the two-dimensional equivalent of an array is a record batch, which you can kind of think of getting a little bit closer to like a data frame. And let me get rid of my null values for now too. You have two columns, column 1, column 2. Here's the data for column 1, here's the data for column 2. And each item in the record batch, or each array in the record batch, has the same number of records. Kind of the final abstraction on top of that is a table. Now a table is specific to PyArrow. Not every implementation or Arrow implementation has the table, but the table basically allows you to create batches and again work in chunks. So it's kind of like the 2D equivalent of a chunked array. You can see here that I've really created this table from two different batches, and you can even look at those batches individually. So the first batch is that, and the second batch is that. I'm using the same data here. But yeah, that's again an abstraction over potentially chunk data that could be anywhere in memory. Now, when we want to start looking at nanoarrow, which does not have a table object, everything in nanoarrow is essentially an array. But you could still think of your record batches and your tables in terms of struct types in Arrow. So here we have a struct array that I'm just going to create. Let me create some fields first, right? So within one array, I can create two fields in the struct, column 1 and column 2. And then if I want to actually create the right? It would look something like this. So it doesn't appear the same as what we're looking at with like a table and a record batch, but it pretty much has the same data, and it kind of is the same, except you see that at least in the Python representation, it's a little bit more raw. You get two children, so you have one struct array parent with child 0 as the first N64 array of 1, 2, 3, and child 1 is the second array of 4, 5, 6. So again, as you'll see when we jump into nanoarrow, we're going to be passing really struct array objects and not really dealing with tables. So let's take a look. If we were to jump in and do that, I'm just going to go ahead and create a second terminal here. We can have that side by side and jump into my code. I might have made this already, but we're working with data frame libraries. We have pandas, we have polars, we need a bear theme, and we're going to create a data frame library that barely does anything. So this thing is going to be called barely. We'll drop that right there. That'll be nice and easy to work with. And yeah, once again, the first thing that we want to do almost all the time when we set up our project is create a virtual environment. So I'm just going to head and create that for now. And while that's loading, I'll get a couple things ready. That's good. We'll go ahead and activate that. And then I'm going to install a few things here. I'm going to install IPython just to have an interactive shell. We'll do PyArrow, pandas, meson. We talked about meson before, and sorry, this should be install. And I'm also going to add CMake here, which we'll talk about why we need that in a couple minutes. Let me go ahead and jump to my project a while. First thing I'm going to create is my meson build configuration. I'm going to just copy and paste what we have here and talk about this for a second. So in the first video that we did, talking about nanoarrow, we built a C project. Now we're going to do C++. I'll show you some of the reasons why. But mainly this comes down to nanoarrow having some nice abstractions for C++, so we don't have to manage memory and could just write code a lot more concisely. I've decided to use the C++ 20 standard. Depending on what you're trying to target, especially today, that might be a little too new. Yeah, if you want a really wide platform, you might have to do C++ 17, but I think most people are fine with C++ 20. And then the rest of the stuff is kind of the same as the last project. We're still using nanoarrow. The other one that we're adding is actually nanobind, and I'll talk about that in a second. But nanobind essentially lets you create Python extensions using C++ really easily. So cool. Now that we have our build configuration for Meson, my pip install was done. I should have Meson available to me as a tool. I'm going to go ahead and create a subprojects directory, and then go ahead and do a Meson wrap install nanoarrow. And while this is running, it's actually going to install, at least today, nanoarrow version 0.5. I'm going to use features that aren't released in 0.5 yet. They are in 0.6. So I need to update that. And 0.6 has not been released yet. So if you're looking at this video in the future, you might be okay having done just what I showed you. But if you ever need to customize a project, you can go into the subprojects folder and look at the wrap file that the Meson wrap install just did. This wrap file is from Meson itself. They have all these presets. I can still kind of take all that and change it and customize it. nanoarrow uses Meson kind of directly. It's built into the project itself. So I've just taken a different commit hash, which is going to be part of 0.6 whenever it gets released. It's just kind of random today. But yeah, I just took this because it's basically what head was at when I started this project. So anyway, the details of that aside, the other project that I want to use, as I already mentioned, is nanobind. And once again, I'm hoping in the future, really soon, that you'll just be able to do Meson wrap install nanobind. If you look at the Meson wrap DB GitHub, I have a PR open for that. It's just not fully complete yet. So instead of us being able to use that natively, we're actually going to wrap a CMake configuration, which is not that difficult. It was just the reason why when we did our pip install command, I had to add CMake. Ideally, we don't need meson and CMake, but nanobind does not use meson by default. It uses CMake, so meson can wrap CMake and get what it needs out of that using a configuration like this. All details aside, this pretty much works for what we need in our meson build configuration. The last thing I need to do is just grab my source barely extension file. We'll go ahead and create that now. Barely ext and .cc for a C file, so that the compiler can kind of auto detect that. Once you have that all set up, you can just go ahead and do your meson setup build directory to have meson download nanoarrow nanobind for you, create a build folder, and once again, just to support the IDE and your code completion, I'm going to grab the compilation database from the build directory and symlink it to my project root. So I'm done there. Once I'm back in my editor, I'm even going to restart my LSP. How to do that depends on which editor you're using. But now that we have that, we can go ahead and start including nanoarrow, nanoarrow.hpp, which is our C++ nanoarrow file, and then we can even include nanobind, and nanobind just has a .h file. And then what we're also going to do is create a namespace alias. So we'll do namespace nb equals nanobind. It's really up to you if you care to do that or not, but I think at least in the CMake examples, they pretty much do that all the time, so we'll just stick with it. The next thing that we need to do with nanobind is create our module definition. If you remember when we did this back in the last video with just a C extension, there was a lot that you had to fill out. You had to create a Python module definition, define the methods that went to that module def, and do all these kind of declarations. Nanobind, it's a little bit easier. You just say nanobind module, use that macro, give it the name of your module, which is barely, and start adding classes or method definitions to your module. So for now, I'm going to create this function called sumChunks, which will ultimately fill in with real data. But for now, you can see how easy this is with nanobind. If I were to just do kind of a small implementation there and do meson compile, I'll be able to use that and do import barely as BL and just do bl.sum 42. Okay, that's the number we got back there. So that obviously is not what we want our implementation to look like. So we once again have to think about like the type of data that we want to receive. And when we were looking at this table before, we talked about how there is an arrow array stream method on the table that kind of allows you to iterate over each batch of the table. We talked about batches. There's two different batches in this table that we looked at. You can see in a list. We really want to go batch by batch, and then within each batch, essentially go column by column. But again, remember that in nanoarrow, there is not really the idea of a column. Each batch is going to be exposed to us as a struct array. Okay. So let's go ahead and see how to do that. Step one is to actually get this capsule and unpack it. When we did this in the last video, we kind of had a lot of steps to use like pyarg parse tuple, check that we got the right thing coming through, the bridge between Python and C. Nanobind makes it a lot easier. You can just say, I just need to get a Python object. This is an argument I'm accepting, which will be this table. Now, I could accept maybe something more strict like a capsule, but then the user would have to send in this to the function. I really just want them to say something like bl.sum table, and I'll look at table as an object, check that it has this method defined, call it, and get the capsule out of that. So we're just going to accept a generic object. So we'll say const auto maybe capsule equals mb get attr. And this is another thing I really like about nanobind. If you have some familiarity with how Python works internally, get attr is a dunder. You'll have table get attr is a just a way of getting attributes from any kind of object. It's essentially what, when you do a call like this and say table dot, I don't know, batches, there's a underlying, let me get something that works, arrow C stream, right? Get attrs is going to search for arrow C stream, grab it, and tell you if it's there or not. So I could just say nanobind from my object that I've received in, look for the arrow C stream attribute. And I also want to invoke that, right? So if I were to just, even in the Python layer, just run this from here, it would give me this bound method. But I really need to invoke that. And what I like about nanobind is that same way of expressing what you're trying to achieve just works in C++ as well. So I can just directly invoke that and start working with this capsule, maybe potentially capsule data. It probably is at this point, but we also just want to double check and now say, okay, go ahead and take what probably is a capsule, and it's coming back as a Python object like all Python C API calls do, and make sure that I can really explicitly cast that to a capsule. It's kind of like doing an is instance in Python, right? Doing an is instance capsule is what we're doing here with the cast. And if that doesn't work, it'll just go ahead and throw an error for us. So we'll toss that there. And by now I've passed the is instance check. I need to actually make sure that that capsule has the right name. If you remember again from the last video, a capsule is really just a void pointer pointing to any kind of storage in memory and a name associated with it, so you can be a little bit more confident with the memories that you're looking at. So we really need to make sure that we get a capsule with the name arrow array stream. If not, that void pointer is not what we expect it to be, so we have to be a little careful. I'm going to go ahead and do this by saying, and actually making a call to the Python C API. You can mix in here with nanobind. I'm going to make this call to PyCapsule get pointer, and I'm going to say take the capsule pointer and make sure that I have this thing. It has the name arrow array stream. Okay, so this is kind of mixing C++ with C code. This PyCapsule get pointer is directly from the Python C API, and it basically checks that your capsule has this name. If not, it gives you null back. So we need to just really check for that really quick. Look for null pointer, and if that is the case, I'm just going to say, okay, go ahead and throw, what should this be? I guess a value error, right? Throw nanobind invalid PyCapsule provided. We can go with any kind of data there. But yeah, that's just our way of checking we have arrow array stream, and if not, we're going to throw an error and jump out. Again, with nanobind, we're not managing reference counting or anything like that. It's just a lot easier to deal with. One last thing that we want to do is start using these C++ helpers from nanoarrow, which a lot of them start with unique, and you can see quite a few of them here. We're going to pick the unique array stream, and I'm going to construct that from the C stream. Now, what do these unique objects do? Well, they are pretty much handles for you, and you can kind of see how they're all implemented, but they basically take an RAII approach to managing these resources. So you don't have to worry about releasing them or having memory leaks. Basically, when they go out of scope, they will clean up the objects for you. We don't need to go into the details of that, but again, I like wrapping that here because once I'm done with this function, or if I have an error and need to, jump out, the unique array stream goes out of scope. It cleans up all the stream things that it needs to, so we don't have any memory or resource leaks. Okay, so we've gotten the capsule. We made sure it's wrapped in a C++ unique array stream object for us. Now what we want to do is actually get the schema from that stream. And when you have a stream of data like we have here with our table, all of the individual batches within that table will have the same schema. So we don't need to go into the different chunks or batches first. We could just ask it with the schemas up front, and that should apply to every single chunk or batch of our stream. So we once again are going to use this nanoarrow unique schema. And if you remember from the last video we did on nanoarrow, schema is kind of something that you build within the scope of nanoarrow. And if you are done building it, you use the schema view to interact with it. So the schema view can help you identify types and other metadata associated with the schema. So it's good to pair them both in this scope. We're also going to create a general stack allocated error message that any of the functions will make use of. And then now that we have those kind of declared, we could start trying to actually extrapolate those items. So the first call I'm going to make is say arrow array stream get schema. And what this will do is basically say from the stream, and I'm going to make this .get call, which gets me the pointer that the unique array stream is managing. And I'm going to make sure that from that I can place that value into the schema, unique schema, and if there's any errors, use this local struct. What's nice about this nanoarrow throw not okay is in C++ it'll just throw an error message for you. Nanobind will catch that and kind of unroll everything for you. So it's an easy way to just bail out and make sure all your resources are cleaned up. Next thing we need to do now that we have the schema is initialize the schema view. Again, the schema view does not own any resources, so it does not need to be a unique thing per se. I just have a local stack struct on the stack for it, and I'll go ahead and get the pointer to the schema, and once again do an error. And with that, we have pretty much extrapolated the schema that we need for our C stream. Essentially, we can now inspect that we have two columns of data within each batch and the types associated with them. Now things get pretty fun, I think, and this is where I really wanted to use a version of nanoarrow that's beyond 0.5 because a lot of this stuff was added after that release. The main thing I'm looking at is this view array stream, which is a really nice abstraction in C++ that allows you to use essentially for loops to iterate over an array stream instead of, a more traditional C loop where you're using an index and you're saying, oh, for I equals 0, I is less than whatever, I plus plus. You can get a really natural for loop, just like in Python, by using this view array stream abstraction. And again, remember that this is going to loop us over the batches, right? So each, batches, let me grab that. We're basically going one by one. You can think of it as a 4 item in batches. It's going to grab this first record batch and then the second one and kind of help you iterate that without having to write that by hand, which is super nice. The next thing that I want to do before we actually get into the iteration is declare my result. So we're basically doing a reduction down to a scalar value. In subsequent videos, we'll probably talk about just adding a column and returning it back, the sum of call 1 and sum of call 2. But for this video, we're summing everything together and just giving one value back, just because it's a little bit easier that way to implement it. And cool, we have that set to 0. Now what we could do is start iterating over each batch or chunk, whatever you want to call it, in our array stream. Again, this is where that view array stream is nice. I could just use my for loop here. And then what I'm going to do on the next line, again, this is looping within each batch. I want to loop by column next. And there's not really a C++ helper for iterating a struct array by its columns just yet. Maybe there will be in the future. But for now, I really just need to do this by position and grab, array 1, array 2 within this struct array that we now have from our first batch. So this is a little bit more traditional of a C loop. This is C++ 20 right here, where I'm going to go ahead and initialize this variable as part of the loop. So I'm going to initialize I using the same type as schema and children. I know it's int64, but I don't know, in case nanoarrow ever changed it or something, the decal type makes it so I don't need to say that. It'll just be inferred from schema and children. I'm going to loop until I get to the number of children there. And this is, again, your more traditional C type of loop. Within each loop iteration, what I can do is also create a unique array view. And once again, the array has the data. The array view allows you to kind of see into it and access it. We used that in the last video. But this is a unique array view, so once this goes out of scope, essentially on each iteration of the loop, it'll clean up the resources for us. We could also declare this outside of the loop and then call reset, I think, within each loop, but this is easier for now. If there's any performance issue with that in the future, I may come back and revisit that. But we need to initialize this array view. Once again, we call .get to get that resource handle. I need the pointer to the schema. I'll go ahead and grab that arrow and error, I'm sorry, and then that should be done there. Next thing we need to do is once again throw not okay. If I cannot set the array data to that, so I'm going to go ahead and grab my array view here. Whoops, I'm sorry, I made one mistake here. Remember that the schema is the top level item here, right? So if I were to do sRarray.schema, I guess that doesn't have it there, but the top level schema here is a struct array. I'm not really interested in knowing that I have a struct array. I'm really looping over the columns, and I need to know that this first column or child of the struct array is int64. And this is why we started this I initializer, because I can come in here and say, okay, well, I need this to actually be the ith child of the schema. So in my first loop, it's in 64, and the second's in 64, but this varied. I'd be able to see that. And again, down here within the array, I'm kind of doing the same thing where I need to say, within each record batch or chunk, however you want to think about it, I need to grab the ith array of data. So this becomes chunk iChild. Once again, we'll use the error message and let that work. So now I've gone through each chunk of my stream. I'm looking at a record batch. I'm going column by column. Once I'm in an individual column, I want to start adding the elements from that column. This is another cool thing that was added after the 0.5 release of nanoarrow, which is a view array as. So for this implementation, I'm assuming everything is integral. Obviously, that's not something you do in production. We'd be inspecting the types, making sure that things are the type we want to be, maybe ignoring it if it's not integral. But for now, I control the sample data. I could just go ahead and assume everything is in 64. So what we're doing here with this view array as is taking the array view and saying, basically treat it like every element within it is in 64. And once you have that done, you can then just say, okay, well, for each record as you iterate through it, within this loop, this value, go ahead and just say, give me that value, or if that entry is null, give me 0. That's the value.value, or there's a couple other ways you can handle that, but again, this value or basically says, if it's null at whatever record in my array, just go ahead and add 0 to my result or skip it. There's a couple ways that you can kind of handle that. But that's pretty much it for the loop. So once we get out of here, we can just go ahead and return our result. That's our extension. That's it. So if I were to go ahead and try and compile this, we could just start working with it. Whoops, IPython. Let's do import PyArrow. Import PyArrow as PA. Import barely as BL. We'll do an actually we need to create a table here, right? That's kind of what we've worked for. So let me first create a record batch. I'll just use the same data I've been using before, and I'll use a table. And this is my table data, 1, 2, 3, 1, 2, 3, 4, 5, 6, 4, 5, 6. If I were to add this all up, I would get the number 42. That's all there is to it. Just like we saw at the beginning of this scales, right? So you don't need to just be working with data sets that are in memory. We'll go ahead and see that. Now this will take a little bit more time, but we really don't need to worry about the fact that, I have this table on my desktop, which is probably over 80 gigabytes worth of integers that I just kind of created. I'm obviously not going to be able to put all 80 of those into memory, but I can just go ahead and memory map it and say, okay, well, create a memory map to this file on my desktop. And once I have that, because I've been using this stream capsule kind of passing thing, I can just go ahead and add that to my sum function. This is, import barely as BL. Let's try that again. And this may take a minute, but you'll see that it loads and gives us a result back. And there you have it, ladies and gentlemen. That is 80 gigabytes worth of data on my laptop while recording a video. Just loaded all from this one extension. So think about that for a second. If you're writing distributed computations or anything that needs to scale beyond your machine, nanoarrow is a great library to use. There's a ton that you could do here. We're still just scratching the surface, so I plan to keep making these videos and showing you more and more features that you can take advantage of. If you have any ideas on things you want to see as we build out our barely useful data frame library and make it more useful, leave it in the comments. Love to hear. And otherwise, look forward to seeing you in the next video. Bye now.